when you're watching it going around in a circle, okay? When you're watching it going around in a circle, because we have depth perception, you can actually see it going around in a circle, right? But what if, let's say, we'll do it for these boys here, okay? What if I start going around in a circle like this? Now, again, we have depth perception, but if you didn't have depth perception, what would you see it doing? They would see it going up and then going down, and then going up and going down, and going up and going down. True? And so it turns out that there's no real difference between circular motion and simple harmonic motion if you just look at it in one dimension. Because it just goes up and then goes down, and then goes up and then goes down. Right? Same thing if I spin it this way. Okay? If I spin it this way, you see it moving left and then moving right, and then moving left and then moving right, and moving left and moving right. True? So we understand it's moving in a circle because we have depth perception, but if you eliminate one of your, or you eliminate the depth, you just see it moving back and forth or just moving up and down. Is that cool? All right. Just a little bit more and then I'm going to stop talking. All right. So here's what we have. If I want to write the position. So the position is equal to the amplitude times the cosine of omega t. The c value tells you how much your thing is shifted left or right depending on the function you're using. We talked earlier in the year, you know how like cosine and sine are just the same function but they're shifted over 90 degrees? So we're going to leave the c value off and assume that when I drew it, this one's cosine. We're going to start off as cosine. Okay. All right. You guys good here? So far so good? All right. What about this one? What about the velocity? So first of all, check your neighbor. What trig function is this one? All right, check with the neighbor. What trig function is this one? See if your neighbor knows. What'd you say? So it's something times negative sine. Well, it's negative something sine, and then you'll notice this is from Friday. We realized that there's some coefficient here, but omega t, it's the same for each one. If you look back at your notes from Friday from the lab, you'll see that after the trig function, you have something times t and something times t. It's the same for each one, correct? That's going to be important. This one is plus 0 because the equilibrium for this one is 0, so that's good. What we need to do is we need to figure out what is this coefficient here. Okay? We need to figure out what this coefficient is here. Now, I'm going to give you a hint. It's a combination of this amplitude for this wave and this angular frequency. So, look at your notes, okay? What kind of combination? Is it multiplication? Is it division? Is it subtraction? Is it addition? Is it division? How are you putting those two things together to get the actual value? All right? Look at your notes and see if your notes have any kind of indication as to what it may be. Luca, do you have your, what was your A value here?
That's a good question. Steve, do you have the picture?
Does someone have one? Does someone have it for us? Go ahead, Kelly.
I have 0.08.
For amplitude?
Yeah.
And what was your omega value?
7.1.
And what was your coefficient here on this one?
It was 0.5.
0.5?
Yeah.
All right. How am I going to put this and this together to get this number? Can I add them? That doesn't make any sense, right? What about subtract? What about multiply? Yeah, if I multiply 0.08 by 0.7 or by 7.1, is that pretty close to 0.5? That cannot be a coincidence, right? You with me on that? So, you guys want to, if you look at yours, are you going to go with like, how's that look? Does that seem reasonable? Yeah.
So then, for the acceleration one, would it be that times 0.5?
Oh my gosh.
Wait, maybe not.
No. I think me has made a significant breakthrough in our understanding of how physics works. I'm not sarcastic. I think that this is really a really smart way to think about this. What she said was, well, let's look at this one then. She said, first of all, let's get what trig function is this one? What's this one? Negative cosine, that's right. So I got negative something times the cosine omega t plus 0 again. What she said was really interesting. She said, then are you telling me that to get this coefficient that goes here, I'm going to take this value and then multiply by this again? Right? That's what she said. And that turns out to be 100% correct. This is negative omega squared a. So, to go from here to here, we take omega and multiply by a to get omega a. And then to go from here, we multiply by omega again, which is so cool. And this is how we got our functions. And if you look closely, okay, if you look closely, if I take this 0.5 and I multiply by my omega again, 7.1, right? I bet this is probably what? In the 3 range? 3?
Yeah,
3, 4?
3.19.
Exactly, right? So I think that's super cool. Okay? I think that's super cool. All right. Now, if you've had a calculus class before, this is going to be interesting. If you haven't, it's not interesting. Objectively, it's only moderately interesting, so don't worry too much about it. What's the derivative of cosine? It's negative sine, which is what we have here, right? But how do I take the derivative if I have an argument here? What do I have to apply? You got to apply the chain rule, right? And so what am I going to do? I'm going to take this, I'm going to take the derivative and then multiply by the argument, and I get omega a. And then what am I going to do again? Take the derivative of negative sine is negative cosine, I'm going to apply the chain rule again, multiply by omega again, and that's how you get omega squared. See how this is super consistent with our understanding of how that works? What's that?
The constant's eliminated, so we take the derivative.
Exactly. That's a great point. He says, look, when I'm going to go take the derivative, I take the derivative of this term. Then I'm going to take the derivative of this term, but the derivative of this term is just 0 because it's not dependent upon t. That's a great point. All right. All right. One last thing, and then I am honestly going to stop talking. I wonder if there's a relationship now between my position graph and my acceleration graph. So what I want to do is I want to write acceleration in terms of the position. Is there a substitution I can make here that's going to give me the acceleration in terms of the position? Check your neighbors. See if there's a substitution we can make here that might be interesting. Do they share any terms where I might be able to make a substitution? All right, check with your neighbors.
Because I think what's nice is that you'll get it's all between each one of them, you'll get a cosine inverse. Plug that into a cosine, it finds out itself.
Isn't it calculus?
This is not a calculus problem. This is not a calculus problem. This is an algebra problem. Do you see something here? Do you see a cosine omega t there?
I do.
Do you see a cosine omega t up here?
Oh.
I do.
Now, what about, oh, it's a. It's a cosine omega. Look at, don't forget the a. So can I just substitute this in then? What that tells you is that your acceleration is dependent upon your displacement. So if your displacement is 0, because you're at the equilibrium, your acceleration is 0. If you're displaced in the positive direction, you're going to have negative acceleration. And if you're displaced in the negative direction, you're going to have positive acceleration. All right. What are we going to do with this information? Here's what we're going to do. I want you all, okay? So you're going to go back to the stations today, okay? Back to the station today. You're going to exchange a spring, get a spring from somebody else, okay? Get a spring from somebody else, and what you're going to do is you're going to bounce that spring, you're going to get an equation for the position, and your goal is to solve for the spring constant, okay? Your goal is to solve, so you're going to use this equation. Now, you're going to get it in terms of sine, but the sine, you're going to get it in terms of sine. That's not a problem because of the fact that you're going to have the same argument omega t here. Okay? The only thing that is different between sine and cosine is the plus c that's here, so don't, it's fine. So get a spring, put a mass on it, get an equation, use this equation to solve for the spring constant. Got it? All right, we're going to say groups you're working on. Working with. All right, let's make this happen right meow.